Hello and welcome to Applied Database 1. This session will be addressing the process of transforming the data model that we did in the past session into a database design. It's important to note that database design will be the final phase before you start coding. So next step will be the coding with the SQL language, where now with the design, changes will be harder to implement at this point. The database design will include all what the data model has. In addition, we are going to add data type, data size, and database constraints. What are the steps of transforming the data model into a database design? The transformation consists of three main steps. The first step will be replacing entities and attributes with tables and columns, replacing identifiers with keys. In addition, column properties will be identified like data type, data size, and other properties will be also identified such as is this column required or can be left blank. And this property is called the null and not null constraint. This information will verify the normalization process. The second step will be creating relationships by placing foreign keys in other tables, and that's another kind of constraint, foreign keys. The last step will be enforcing integrity constraints to ensure consistency and data integrity. And that will be using the minimum cardinality with the optional mandatory requirements. To write the entity in the form of a table, it will be expressed as the employees. As you can see here, employee, this is a table, and employee number is the identifier, and we can underline that. And then we have the employee name, phone, email, hire date, review date, and employee code. So this is a form of writing. This is how we write, but usually we would like to express that in more of a graphical representation, as you can see in this one. So on the left hand side, you can see the model, the data model. In this case, we have the employee entity. So this is an entity, and the identifier is employee number, and those are the attributes. On the right hand side here, you can see how we transformed the model into a table. So now it's called employee table, and we have the employee number as primary key, and the rest is the columns that should be created within that table. So we have the attributes being translated or transformed into columns. And you can see that just to understand the difference, or just to recognize the difference, we have this with a shadow. We added the model with a shadow, while the design does not have shadow. Remember, in previous sessions we addressed candidate keys, and candidate key can be also called alternate keys. So we are using these to select or elect from them a primary key. So alternative keys or alternate keys can be identified to select one of the those keys to be the primary key for my table. If none of them work, we create our own surrogate key. Those alternate keys are identified in the design with AKNM. So alternative keys, so AK, and then notation of the N, where N is the number of the alternate key and M is the column number in that alternate key. If you look at those tables, can you specify candidate or alternate keys in the employee table? In this case, we have one alternate key, which is the email in the employee, while we have three alternate keys in the customer table. One of the main important properties of a column is the null not null constraints, which means is this field or column required or not. Adding this property will allow people to leave some fields empty or enforce um, filling those fields. That can be identified in the database design by adding either the null or not null in front of these columns. In the example here, you can see that employee name will be enforced to fill while or to complete, while employee phone can be left blank. Employee name not null, phone can be null, email can be null, and so on. Other properties that should be identified in the design are the data type and data size. This slide shows some of the common data types used in Oracle. We have the character, variable character, date, binary, number. And just, those are the most common used, but there are other types that we will show in a minute. And as you can see, we added those in front of the column 2. So now we have the data type, data size, and we are going to add if they are alternate key or not, and we are going to add the null and not null constraints. So this slide and the next slide will list some of the common data types and the associated data size that's identified in Oracle. We will be dealing with Oracle, so those are the data types in Oracle. You can let the database management system provide a default value for a certain columns. This slide shows some of the examples of default values that can be added. Through column properties, we can add constraints that will limit data values in that field. For example, domain constraints, column value must be in a given set of specific values. Range constraint, column values must be within a given range of values. Interrelation constraint, column values are limited by comparison to values in other columns in the same table. Interrelation constraint, column values are limited by comparison to values in other columns in other tables. And by doing this, we are enforcing referential integrity constraints on foreign keys. So the values of this table should be similar to values in another table. As we learned in a previous session, those tables should be normalized, means split into meaningful entities and have no multi-valued numbers in the same cell. Of course, the PCNF is the normalization where you split the tables or the entities, and the for normal form is the one that will ensure that I don't have multi-valued numbers in the same cell. To create one-to-one strong entity relationship, we place the key of the first table in the second table as a foreign key, or the other way around. Either design will work, no parent, no child. Don't forget to identify the minimum cardinality of the relation, which is the mandatory to optional relationship. This slide shows an example of creating relationship between two strong entities such as the club member and the locker. This relation can be created in two different ways. Either a member number as a foreign key in the locker table, or the locker number as a foreign key in the club member table. So either one will be correct. To create a one-to-many strong entity relationship, we place the primary key of the table on the one side of the relation into the table on the many side of the relationship as the foreign key. The one side is the parent table and the many side is the child table. So basically place the primary key of the parent as a foreign key in the child. This slide shows an example of creating a relationship for a one-to-many strong entity relationship such as company and department. Each company has many departments. It's a one-to-many relationship. In this case, the parent is the company, um, which is the department is the child. So to create the relation, we place the primary key of the company, which is company name, as a foreign key in the department table. To create many-to-many strong entity relationship, there is no place for the foreign key in either table. A company may supply many parts. A part may be supplied by many companies. So what's the solution in this case? The solution is to create an intersection table that stores data about the corresponding rows from each entity. The intersection table consists only of the primary keys of each table, which form a composite primary key. Each table's primary key becomes a foreign key, linking back to that table, to the main table, to both main tables. So the company uh, part um, intersection will have company name and part name both as primary keys, and that's why we underline that. So this is the new table, or the notation of the new table. And this is how the data model will look like, or the database design. Since it doesn't have a shadow, it's a database design. So the database design will look like that. And this is what we are learning. We are learning to transform the model into database design, knowing the different tables that will be in the database, knowing what will be the primary key, and what are the columns that should be inserted or added to each entity. Creating a relationship or relationships using ID dependent entity. There are four uses for ID dependent entities. Representing the many-to-many relationship, we just discussed that. And then we can create association relationship instead of intersection, and we'll talk about this in a minute. And then we have the multi-valued attributes, and we have the archetype or instance relationships. So what's the difference between intersection table and association table? We already explained the intersection table and how it contains only the primary key of the two entities as a composite primary key and as a foreign keys, while the association table has the primary key of the two entities, which is as composite primary key and as foreign keys, plus it has one or more columns of attributes specific to the association of other two entities. To create a quote, we can add association table that will have the primary keys of the two entities. So we have as a composite primary key, we have the part number and the company name. Those are the primary key. The combination of them is the primary key. Now remember that those are foreign keys that will link this new association table with the two main entities, the part and the company. Then we can add the price within that quote um, as a new attribute or as a new column actually with this design. So now we have another column that's been added, and that's why we call it association, which is more than intersection. What if we have a multi-valued attribute? As we stated before, we use the fourth form and separate these values of a new entity which will be covered or converted to a table. In this example, we have a company with multiple contact information. A new entity was created called phone contact, which will include the contact and the company name as a composite primary key and the phone number as an attribute or as a column. So we have the model on the left hand side and the design, database design on the right hand side. If the entity has an instance pattern, then a new instance table, which will be also called archetype, can be created to list the different instances and their attributes. A good example is a classroom or a class, which has many sections, and the section is an instance that will include the professor name, class days, and time. Each section will have different time, different days, and might have different instructor. Using the class name in the instance table will make it an ID dependent table. If the section is a weak entity but not ID dependent, that means that the class name is not mentioned in the section, then the primary key will not include that class name, but reference number that connects the section with the class will be added. So now we have a reference number as the primary key, and still it connects to the class name through a foreign key down here. This slide shows the data model of a mixed entity relationship, where the sales order number is used as a part of the primary key of the order line item and as a foreign key for the sales order table. On the left is the data model, which was translated to database design on the left. And as you can see, the item number here is used as a foreign key to connect the order line item to the item table. In this mixed entity relationship, the skill name was used as a foreign key, but a skill number was added as part of the primary key for the employee skill table. Again, the data model on the left, while the database design on the right side. Subtype relationship can be represented as depicted in the model as shown here, then translated into design on the right. An employee can be a manager or a database admin. In both cases, the employee number will be used as the primary key of the subtype table and is the foreign key for the employee table. A recursive relationship occurs when an entity type has a relationship with itself. This example shows the data model that represents boxcar of a train database, where each boxcar related to the other one, either behind it or in front of it. Except for the first boxcar, you can see that there is a relation between the front and the back. Thus, the relationship is one-to-one between each boxcar and the other, with an optional relationship for the first and last cars. For a recursive one-to-many relationship, let's take the example of an employee who's also a manager, but a manager is also an employee, um, whose details will be held in the employee entity. To implement this as a foreign key, or a foreign key of the employee name manager will be used as a foreign key in the employee table. So we can use that um, as an indication of the manager. In a many-to-many recursive relationship, once we convert the model into a database design, we use the part name as a foreign key in the part integration table. The part will either contain other parts or uh, will will be contained in another part, and that's why we have this kind of a loop. So either this part contains this part, or uh, it will be contained this part will be contained in another part, and that's why we have again this kind of many-to-many recursive relationship. The ternary and higher order relationships may be constrained by the binary relationship that comprise them. For example, we have the must constraint, which requires that one entity must be combined with another entity in the ternary or higher order relationship. And we have the must not constraint, which requires that certain combination of two entities are not allowed to occur in the ternary or higher order relationship. And the must cover constraint, which is a binary relationship, specifies all combination of two entities that must appear in the ternary or higher order relationship. An example of the must constraint: a salesperson number 20 is assigned to customer number 2000. So when creating an order table, which is now a third entity, and that's why we have ternary, the only number allowed to be listed in the order table is in this area where we are missing here is number 20. So only 20 is allowed here. Only 20 will be added here. Why? Because we have customer 2000, and those constraints we got it from the other tables here. For the must not constraints, and in this example, we have two drugs, 20 and 45, which can cause an allergic reaction to customer number 2000. With that being said, neither 20 nor 45 should be prescribed to that customer. So I have 20 and 45 are the allergic drugs, or the allergic drugs that can cause allergic reaction to customer number 2000. So when it comes to customer 2000 and in prescription table, I cannot prescribe for them neither 20 or 45 because they have allergic reaction to it. So must not must not be there. So that's another constraint that we can get from the other two table in the relation. In the must cover constraint, if tasks number 2001 and 2002 can be covered by repair number 20, then the invoice created must cover the repair done on those tasks for that 2002, and it should appear in the missing cell down here. So 2002 must appear here because 20 and 20, which is the repair number, can cover 2001 and 2002. And again, we got that from the other two relations. So with the ternary relation, we can define what number to put here. Relationships can have one of four minimum cardinalities. So now we address the converting the model into design. We saw some of the exceptions and rules and constraints when we create that design, and mostly related to the maximum cardinality. How about the minimum cardinality? So we have those relation. We have both parent and child could be optional, parent mandatory and child optional, parent optional and child mandatory. Both parent and child are mandatory. Um, so in those situations, we have for the optional to optional, no actions will be needed to do to be done at that point. The remaining relation has restrictions on the insert. If you want to insert data, add data, or update or delete activities, there are so many restrictions that you need to pay attention to when you do that. So remember, when you write a code and have those types of relations, that inserting and deleting might generate an error message, and you need to write the proper code to address that. Cascading is used in conjunction with the on delete or on update, which means that the child data is either deleted or updated when the parent data is deleted or updated. Cascading update occurs when a change to the parent primary key is applied to the child foreign key. Surrogate keys never change, and there is no need for cascading updates when using them because they are not related. It's a key that I added to the database just to identify it. Cascading delete occurs when associated child rows, the rows are deleted along with the deletion of the parent row. For strong entities, generally do not cascade delete. For weak entities, generally do cascade deletes. That will be fine. This table lists the action required, or the actions required when the parent is required. So you can see that those are the action. If you are inserting, then none. If you need to modify the key or foreign key, then change children foreign key values to match the new values, so that you are cascading the update. And if you delete, then delete children, cascade delete, and you can prohibit the delete if you want. While this table lists the actions when the child is required. So we said mandatory for the previous one. The parent is mandatory, the child is optional, while for this one, the parent is optional and the child is required, and those are the actions that we are allowed when insert or modifying or deleting. This slide shows a summary of the actions to apply in different cases of minimum cardinality, and you can see that in the optional to optional there is no actions needed, and here you can see the different actions or different remarks that's needed. The example in this slide shows how to implement actions for the mandatory to optional relationship. In this example, the department is the parent while the employee is the child. Actions that can be implemented on the parent entity are as follows. Department rows can be created. Department primary key, cascade update if not surrogate key. If a department is deleted, do we delete the associate employees? This is a question that we need to ask. So if yes, then cascade delete. If no, then prohibit the association with the employees. while action on the child will be set referential integrity constraint and set foreign key to not null. A new employee must have a valid department or disallow the insert. Employees can be reassigned to a different department if a valid department or disallow the update. Employee can be deleted. Another example of the department as a parent uh, was optional and employee as a child entity was mandatory. With this scenario, there must be at least one child row for each parent at all times. Actions on parent department rows can only be created when a relationship is created to a child row, requires a trigger. So it will alarm us and tell us that something happened or something being created. We have department primary keys can only be updated if at least one employee foreign key is also updated and also requires a trigger. And we have, can a department be deleted? If yes, then it's the employee who is required. While actions on a child will be, it's okay to insert a new employee. There must be one employee for each department. You cannot change employee foreign key department if last employee in the department, and cannot delete an employee if last employee in the department. A third example, if the department and the child entity were both mandatory, all of the previous mandatory to optional and optional to mandatory actions will apply at the same time. This will create a conflict that requires careful programming to avoid or fix the problem, such as if a new department insert will run trigger that tries to create a new employee, but the employee row is checked by the database management system for a valid department before the transaction is completed. And if we try to delete a department with any employees, we will find that trigger or employee delete will not let us delete the last employee. So we cannot delete the department. So with these conflicts, we need to know how to work that in the database, and when we create the code or when we write the code. So after understanding the concepts of minimum cardinality, we can translate those relationships into a database design as depicted in the figure. So in this example, the company is the parent, the department is a child, and also the employee is a child for the department. So it's all in one relation, and you can see the mandatory to optional, whether we have mandatory for the company, optional for the department, mandatory for the department from this side, optional to the employee, and we have the mandatory to mandatory for the phone contact for the company. So with this, we translated the data model that we created in the past session, in the last session, to a database design. Tables, primary keys, columns, and we know the alternative keys, we know the data type, data size, and we know the null, not null constraints. So all that will be added, and based on that, we can create the code that will be used in the database management system. That will be all for this session. Thank you and have a great day. If you have any questions, please let me know. Thank you.